My name is Chris Dorbian from the US FAA Office of Environment and Energy. I'm excited to chair this session on environment and energy efficiency. We have 3 really great papers, and the first will be jointly presented by Sandeep Bandranath and Emily Jobak. Sandeep is a research scientist at Cambridge Mobile Telematics. He recently earned a PhD from the Department of Aeronautics and Astronautics at MIT, and his thesis focused on developing queuing models for airport surface operations. And Emily Jobak is an associate staff member in the Air Traffic Control Systems Group at MIT Lincoln Laboratory, and she has a BS in Applied Math from the University of New Hampshire. So if Sandeep is able to bring up his presentation, I'll hand it over to you. Great, we can see it.
Sounds good. Yeah, Emily, yes.
Thank you. Hi, everyone. My name is Emily, and I'm going to be tag teaming this presentation with Sandeep. And I'll be discussing our work on spatial modeling of airport surface fuel burn for environmental impact analyses. Next slide. So there are many stakeholders that need accurate fuel burn predictions. I have a couple of examples listed on this chart here. One would be airlines, who would need such a tool to be able to determine the cost in fuel for an airport procedure change. Another example would be airports, who would need such a tool to be able to assess the impact of emissions on the surrounding community. And another example would be the FAA or EUROCONTROL, who could use such a tool to perform network efficiency studies. As understanding environmental impacts of aviation becomes more urgent, the precision to which these models predict fuel burn and emissions becomes more important. So we can go to the next slide. So there are many commercial and government tools available that predict fuel burn and emissions. I have a couple of the more widely utilized models listed on this slide. So the first is the FAA's Aviation and Environmental Design Tool, or AADT. This is the US standard model for environmental impact analysis. It models aircraft fuel burn, emissions and noise and effect on air quality. And similar to that is the EUROCONTROL Advanced Emissions Model, or AEM. This one also calculates fuel burn and emissions for aircraft. And likewise, 2 other models listed at the bottom here, the EUROCONTROL Base of Aircraft Data, or BADA, and the LISI's P&OX model also model aircraft performance. All these models focus on estimates during the flight phase. So there is a need that exists for developing a more enhanced model that focuses on surface operations. Next slide. The goal of our project was to develop an enhanced surface model that predicted fuel burn and emissions. As current surface fuel burn models make some simplifying assumptions, and this affects the accuracy of their predictions. There's been recently an increase in operational data availability, and specifically, this is the time series data in the flight data recorder data sets. And this combined with more modern analysis techniques provided us an opportunity to develop more accurate models. So our goal for this analysis was to model the amount and location of fuel burn and emissions for environmental impact assessments. Next slide, please. As we continue to work on this program, there's been several phases of the analysis. In the next couple of slides, I'm going to go over a summary of all the previous work that we've concluded, and then I'll pass it off to Sandeep to discuss some of the more recent analysis, which is on spatial distribution of fuel burn using our airport queuing model. And once you know the spatial distribution of fuel burn, you can then combine that with statistical models to look at airport emissions dispersion. Next slide. So previously, the goal of the analysis was to develop an enhanced prediction for aggregate fuel and emissions estimates on the airport surface. So this top diagram shows the current steps used to calculate these aggregate values in a model like the FAA's ADT model. So the fuel burn rate is determined by aircraft type, and this value is taken from the ICAO engine certification data bank. And this is multiplied by a taxi out time. And this taxi out time is either taken from the landing and takeoff cycle, which assumes 19 minutes of taxi out, a user specified taxi out time, or empirical data for an airport. So this taxi out time is multiplied by the taxi fuel burn rate to get the total surface fuel burn. And an emissions indices is then multiplied by that total surface fuel burn to get the total surface emissions. Our approach to this applies 3 enhancements. The first is to the taxi fuel burn rate. The second is to the total taxi time. And then the third is to the pre-taxi fuel burn. So over the next 3 slides, I'm going to go over in more detail the analysis that was performed to obtain these enhancements. So next slide. So the first thing we looked at was enhancing the taxi fuel burn rate. So using the data that we had from the flight data recorded data set, this contained information on the fuel flow for the aircraft. So we took the mean baseline fuel flow rate and regressed it against the ambient temperature and pressure to develop these proposed models for each aircraft type in our data set. Those proposed models are summarized in this table at the bottom of the chart, where each row of the table corresponds to a proposed model for an aircraft type. You'll see the 4 rightmost columns in this table summarize the error between our proposed models and the ADT model. And you see that for some aircraft types, the reduction in the mean absolute error is up to 93% for some aircraft types, which is pretty significant. Next slide. So the next thing we looked at was enhancing the total taxi time. So as I mentioned in an earlier slide, this taxi time that's currently utilized is either the LTO 19-minute taxi out time assumption, user specified assumption, or outdated airport specific taxi times. So what we did was we updated these taxi out distributions for major US airports. And we did that using data from the FAA's ASPM data set, and that contains flight level taxi out time information. We took that taxi out time information and aggregated it by airport using recent dates. And that analysis is summarized in the plot below, where these box plots, each box plot represents the distribution for the taxi out time for an airport. The red line in each of these boxes represent the median taxi out time for that airport. And then the dashed line that goes across the full plot represents the 19-minute taxi out simplification used by the LTO cycle. The error between using that 19-minute simplification taxi out time compared to the actual mean taxi out time for an airport is shown as the red percentages above each box plot. And you can see that error can get as high as almost 73%, depending on the airport. Next slide, please. So the final thing that we looked at was incorporating pre-taxi fuel burn, which is currently not considered in the ADT model. So we did this by using the flight data recorder data set, and from there getting the engine fuel burn for each aircraft type. In addition to the engine fuel burn, we also considered the fuel burn from the APU. And to estimate the APU fuel burn, we looked at ACIRP reports to determine what an APU fuel burn rate was, as well as getting information on how an APU is used by talking to a commercial airline pilot. So we had the APU fuel burn as well as the engine fuel burn for the aircraft when it was at the gate during pushback and during engine startup. And then those total pre-taxi fuel burn distributions are shown in the ascribed plot, where each solid line represents the pre-taxi fuel burn distribution for each aircraft in our data set. We then found that there was a very strong correlation between the pre-taxi fuel burn and then the maximum takeoff weight for the aircraft type. So we use that relationship to then predict what the pre-taxi fuel burn should be for aircraft types that weren't in our data set. And those are shown as the dashed vertical lines in that same plot. Next slide. So here I'll hand it off to Sandeep to discuss these the next steps in analysis, which was spatial distribution of fuel burn using airport queuing model.
Thanks, Emily. Thanks for presenting the background and our prior work on enhancements to inventory analysis that is intended to improve the accuracy of aggregate fuel burn and emissions in the taxi phase of flight. In addition to those aggregate quantities, one is also interested in spatial distribution of fuel burn and emissions at an airport. I'll be talking about that in the next few slides. Spatial distribution of emissions and fuel burn are needed for assessing the environmental impacts on communities near an airport. Using spatial distribution, one can evaluate dispersion of emissions in the vicinity of airport, and it can also be used to model taxi noise as well. We present two approaches. One is an ideal approach, and the second one is a practical approach that we follow. The ideal approach is shown in the flowchart on the top, and the practical approach is shown in the flowchart on the bottom. So ideal approach is a case wherein we have access to flight data, recorder data, or the FDR data or black box data. FDR data contains trajectories of individual flights, as well as fuel flow rate into the engines. With this data, if we have this data for all the flights, then we can compute the actual fuel burn at each location on the airport surface. And we can multiply the emission indices with the wait time in each location to get the emissions at each location on the airport surface. And then you could use a dispersion model to analyze the dispersion, right? However, FDR data is not readily available. Airlines don't share FDR data because of privacy concerns. Even if FDR data was available, regulatory agencies such as FAA and EUROCONTROL, they're interested in performing what-if analysis for future operational scenarios. What-if analysis could be like, what would be the traffic patterns when there's change in schedule? What would be the traffic pattern when there's change in infrastructure and so on? To do such what-if analysis, we need a different approach. And we are proposing the following practical approach to do such analysis. So in our analysis, we use a queuing model to estimate the traffic patterns on the airport surface. The queuing model is a function of the demand, which is like the airline schedule and meteorological patterns, meteorological parameters and airport layout and so on. And it outputs the wait time of flights and different locations on the airport surface. Once we have the wait time at different locations on the airport surface, we can multiply it by the baseline fuel flow rate that Emily talked about to get the estimated fuel burn at each location on the airport surface. Then we can follow the rest of the pipeline that I told earlier, right? So let us next look at what is this airport queuing model, how well it performs, and how does this fit in. In the past, we have presented a few papers on queuing model for airport surface. We have presented papers on theoretical background as well as applications of the queuing model for airport operations. In this work, we adapt the queuing models for operations at LAX. We picked LAX because it's one of the top 5 busiest airports in the world in terms of both the passenger movement as well as aircraft movements. And the other reason why we picked LAX was because we had access to pollutant concentration data very close to the airport, which was helpful in developing models for dispersion of pollutants. For LAX, we looked at the west flow runway configuration that accounts for about 90% of the operation. In the west flow configuration, runways 24L and 25R are used for departures. You can see that in the airport diagram that I've shown on the left. And 24R and 25L are used for arrivals, for landing. And the first step in modeling an airport surface using a queuing model is to look at the traffic patterns and to pick identify the traffic hotspots or the congestion hotspots. We do that using airport surface surveillance radar data or ASDX data. So we looked at ASDX data and found out the traffic hotspots, and that is shown on the plot on the diagram on the right. The brighter areas, the yellow areas, are areas wherein there is congestion on the airport surface. That is, aircraft spend more time in those areas. So what you can see here is, you can see those brighter areas close to the 2 departure runways. And the way we represent the departure process for this particular airport is that aircraft, once they are ready to push back from their gate, they taxi unimpeded, wait in a queue, departure runway queue, and then they take off. So the total taxi out time is given as the unimpeded time plus the wait time in the queues. The wait time in the queue is modeled as a function of the airline schedule, meteorological data, as well as other parameters. Details of that is given in the paper. I don't want to go into that, but let's look at some of the validation plots. Shown here is a comparison between model prediction and the operational data at LAX for a particular day from test data. The plot on the top shows the queue length for the departure runway 24L over the course of the day. And the plot below shows the taxi out time averaged over 30-minute intervals over the course of the day. The red is the data and blue is the model. Overall, you can see a good match between the data and the model. In addition to validation for a particular day, we have also computed aggregate statistics over multiple days or thousands of flights. And what we see is that the mean error and mean absolute error are small relative to the mean taxi out time. So this works well for LAX, and we have also developed and validated the model for other major airports in our previous works. So we have done this for major airports in US, Europe, as well as Singapore in Asia. But one thing to keep in mind is for each airport, we need to look at the traffic patterns using surveillance data or ASDX data and identify the congestion hotspots and pick an appropriate queuing representation that represents the traffic hotspots. For example, at Newark Airport, we found out that the congestion just happens close to the departure runways. So we modeled it with a single departure queue. Whereas at airports such as Charlotte, we found out that you have congestion at multiple regions, such as in the ramp area, as well as departure runways. So we need to pick an appropriate queuing network topology. So overall, we have done this validation process for a few select airports. But the question is, would it work well for all the airports, right? And developing a queuing model and validating the framework for each and every airport would be infeasible. So the question is, can we come up with a more smarter way to do this, right? So we used a sort of a clustering-based approach to do this validation. Using clustering, we determined groups of airports with similar features, and then we validated the queuing model for select airports in each of those clusters. For features, we picked statistics of taxi out delay. This could we picked mean, standard deviation, and skew. Mean taxi out time that represents how big the airport is, how congested the airport is, number of runway configurations, and percentage of operations in VMC that reflects the sort of the weather at the airport. So using these features, we clustered the top 30 airports in the US into 7 clusters. And the table on the right shows those 7 clusters, the airports belonging to those 7 clusters. And the diagram on the left shows the mean feature value for each of the 7 clusters. So let's pick one. Let's pick cluster number 7 that corresponds to JFK and LGA. These are the 2 New York airports. They are very congested. So in the diagram on the left, you can see that the mean delay and the delay statistics are high for the New York airports, and percentage of ops and VMC is also low. Whereas for airports somewhere in Phoenix, cluster 6, you can see that it's less congested and the parameter values are lower. The delay parameter values are lower. We essentially have a queuing model for airports in each of these validated queuing models for airports in each of these clusters. There are other models in the literature that have validated for each of the airports in at least an airport in each of the cluster, thereby validating or generalizing the queuing model across all the airports. So I presented a way wherein we can estimate the traffic patterns given airline schedule and other meteorological data, using which we can now compute the wait time of aircraft in different locations on the airport surface. We can multiply the wait time with the baseline fuel flow rate to compute the fuel burn at each location. Then we can multiply the emissions index to get the emissions at the location. The next question is, what about dispersion of emissions to the vicinity of the airport? So to do that, I'm going to present a statistical model. So the question is, can we infer dispersion of emissions using traffic data and other parameters around the airport in the vicinity of the airport? So to do this analysis, we looked at operational data from LAX. We have an interesting data source from LAX. So we have 4 monitoring stations close to the airport. They're located about 500 to 5,000 feet away from airport walls. And we have pollutant concentration data. That is, we have data for SO2, NOx, CO, CO2, PM2.5, and ultrafine particles recorded for each minute at each of these 4 locations. Just to illustrate how the variation concentration data looks like, I plotted some data and shown here. This is the plots here show the median value of CO, SO2, and NOx over a 1.5 month period. Let's focus on one of these. Let's focus on the NOx data, the third one, versus time. If you look at this plot, you can see something interesting. You see that the pollutant concentration data are higher during the nighttime compared to the daytime. This does not reflect the trend in traffic. The trend in traffic is higher traffic during the daytime. So for some reason, the pollutant concentration data, the pattern does not follow the traffic data. So initially you're wondering, are we doing something wrong with the time zones or something like that? Are we plotting it wrong? But actually this is the right plot. And the reason for this is the variations in the LA regions are influenced by photochemical reactions due to smog formation. And there are other background sources which influences the pollutant concentration that is recorded in each of these monitors. So we need to pick some other signal to correlate correlate or isolate aviation emissions. And the question is how to do this. So we looked at other pollutant concentration data and found out that ultrafine particle number concentration is a promising candidate. Just a brief background on ultrafine particles. Ultrafine particles are those particulate matter that have a diameter lesser than 0.1 microns or 100 nanometers. You would all have heard of PM2.5. PM2.5 are particulate matter lesser than 2.5 microns. So ultrafine particles are much smaller than PM2.5. It's like we're looking at lesser than 0.1 microns. Currently, there's no regulation on ultrafine particles, but recent studies have shown that they can have serious health consequences or health impacts. What we found out was that ultrafine particle number concentration are a very good signature for airport or airport traffic levels or aviation traffic. To illustrate that, I've shown a plot here. This is the normalized ultrafine particle number concentration as a function of time at one of the 4 sensors. I'm looking at particle number concentration between 10 and 20 nanometers, and that is shown in red. And the black curve represents the total aircraft counts, that is departure plus arrival counts for each of those hours. You can see a good correlation between ultrafine particle number concentration and the aircraft movements. The other interesting about ultrafine particle number concentrations are listed here. That is, the particle diameter depends on the thrust setting. So this sort of helps us isolate taxi emissions from other phases of flight. And also the particle diameter for aircraft emissions is much lower than vehicular traffic emissions. So we can sort of isolate other background sources such as vehicular traffic and just analyze the emissions from airport and aviation sources. So this is great. Now we can sort of correlate a particular pollutant concentration with the aviation traffic or aircraft traffic. The question is, can we model this and can we get accurate models? So that is what I'm showing here. That is, the question is, can we estimate ultrafine particle number concentration as a function of traffic, meteorological data, and so on? So one would expect that the concentration would depend on the wind, right? So if you have more wind, you'd have more dispersion. So we need to account for wind patterns and so on. So we developed 2 models. One is a temporal model, and the other one is a spatial model. In the temporal model, we sort of try to estimate the ultrafine particle concentration at a particular sensor using training data from the same sensor. That is, we model the concentration as a function of traffic counts weighted by its fuel burn index of the aircraft, the wind, temperature, and other meteorological data. And whereas in the spatial model, what we do is we train the data using data from 2 sensors and try to estimate ultrafine particle number concentration at any location in the vicinity of the airport. So this is a more general model. The spatial model is more general because we are able to estimate at any location on the airport. So in this model, the In addition to the features that we use in the temporal model, we also use the relative distance between the source, where the queuing happens, and the monitoring point, as well as the direction of the wind and so on. In addition, we also include time delays for advection of pollutants from the source to the monitoring points. So I don't go into details of the model here. More information is in the paper, but let's look at, again, some validation plots using this model. So the regression function was obtained using Gaussian process regression, and shown here is the validation results on a test set. On the left is the validation for the temporal model, on the right is a spatial model. The red is the data, and blue is our proposed model. You can see overall, qualitatively, there's a good match, and the error statistics are shown below. And what we found out was that temporal model performs better than the spatial model because we are essentially training and testing on the same monitoring site. But the spatial model is more general, it'll be more helpful. And we also found out that the spatial model performs better in the downwind sites than the crosswind sites because of the wind pattern. But the key takeaway from this is that the ultrafine particle concentration data is sort of a good signature for aviation traffic or aviation emissions. And we can model ultrafine particle concentration as a function of the traffic and other meteorological data. So quick summary. At a high level, what you're doing in this work is that we are trying to get a spatial distribution of fuel burn and emissions around at an airport. And to do this, we sort of developed a queuing model to estimate the amount of wait time of aircraft at different locations on the airport, essentially estimate the traffic patterns on the airport surface as a function of demand, that is the airline schedule, as well as weather, that's like VMC meteorological conditions. So once we have a queuing model, we can sort of estimate the wait time of aircraft at different locations. Then we can use the fuel burn indices and emissions indices to get the fuel burn and emissions at different locations on the airport surface. Then I also presented a statistical model using ultrafine particle. I presented a statistical model to understand the dispersion of emissions. For this, we use ultrafine particle number concentration as a parameter to estimate, because we found out that ultrafine particle number concentrations had good correlations with the airport traffic, unlike other standard pollutant sources that were significantly influenced by background sources. And we developed and validated these models using operational data from LAX. Some limitations and some things to note. The models, these data-driven models largely depend on the quality of data that we have. But unfortunately, we don't have a lot of emissions data, emissions monitoring data in the vicinity of an airport. The EPA sensors are often located far away from the airport, and they have a resolution of about an hour. We are interested in more finer temporal resolutions to capture the variation in traffic and so on. So that is not available. So we need some campaigns to collect more data. The other thing is the limited availability of FDR data. Ideally, we would like to have few representative FDR data samples for each aircraft type that is operational to get the baseline fuel flow rate. Unfortunately, we don't have access to FDR data for each aircraft type. And for LAX, we modeled LAX using only departure runway queues. But you can have airports wherein, in addition to departure runway queues, you can have congestion in different regions on the airport surface, such as runway crossing area, ramp area, and so on. But I've shown in my previous work that you can model traffic patterns in such more complicated airports using a queuing network, and one can perhaps use that here. And one needs to be mindful of infrastructure changes at an airport. So if there is an addition of runway, you can see changes in traffic patterns. So you need to appropriately update the model parameters and queuing network topology, keeping in mind changes in infrastructure. Some interesting research directions. So in this work, we focus on ultrafine particle number concentration and estimating ultrafine particle number concentration, primarily because they exhibited good correlation. But the question is, what about other standard pollutants, right? So people are interested in NOx, CO2, the PM 2.5, and so on. Those are like the standard pollutants that people are interested in. So to answer that question, it'd be interesting to sort of develop a model that sort of maps between ultrafine particle number concentration and other standard pollutant sources. And the other thing is, in this work, we presented a separate queuing model and a separate emissions dispersion model. So it'd be good to integrate these two together and for inventory and dispersion analysis for airport environmental impact assessment. These are two interesting topics for the community to look into. Finally, I would like to acknowledge Joseph DiPardo and Mohammed Majid from the FAA Office of Environmental Energy for supporting this work, and even Ted Tasher from WLP, who's supporting us trying to try to implement some parts of this in AEDT. So they have been helpful through many discussions. And with that, I'll just stop here and happy to take questions.
Great, thank you very much, Sandeep and Emily. So yeah, reminder, you can use the Q&A feature to enter questions. We have about 5 minutes, and I do not see anything in there right now, so I will take the opportunity to ask a question of my own. So you talk about developing this capability for what if type situations and for generally for environmental assessment and review after the fact, but I was just wondering if you could foresee any sort of real-time application for these modeling techniques, either to avoid certain environmental impacts, maybe by taking into account, current traffic and weather, and trying to avoid pollutant concentrations in certain areas around the airport, or from more of I guess, a traffic management standpoint. Do you have any thoughts on that, or is that anything you've thought about before?
Right, that's a good question. One of the use cases for AEDT is when they're like adding a new infrastructure, such as when they're building a new runway or taxiway. They want to understand the impact of that on the environmental as well, right? So they run multiple simulations to understand the traffic patterns and then estimate emissions and so on. So what we are trying to do is try to improve upon that. So if you have a new runway or a taxiway, or if you have a new runway, you can sort of have a representative queuing model with a new runway, and then you can estimate the congestion with the new runway, and then sort of estimate the environmental impacts. So the primary reason for this exercise is to sort of help in the direction that you have pointed out.
Yeah. Okay. Thank you very much. Yeah. No,
hope that clarified. But with regards to real time, I'm not sure. Probably, what is your question on the real time? I probably missed that.
So, assuming if you knew the weather, the winds, predominant winds, you knew if you were observing certain hotspots on the surface, could you and you would be constrained in doing this, obviously, but could you reconfigure your surface movements in a way that minimize the environmental, the dispersion of pollutants onto communities around the airport? Or if you could direct it such that you weren't dispersing those pollutants on neighboring communities, but maybe on other spaces or on the airport itself, something like that.
Yeah, in theory, I think it's possible, since we have a model for the traffic movements as a function of traffic movements for each runway configuration as a function of airline schedule and weather. We can sort of estimate the traffic movement for each particular runway configuration and estimate the impact on the environment. In theory, this is possible to do, but I don't know how practical it will be to change the operations, like changing runway configurations in real time. So I think in practice, I don't know how that will be applicable, but at least in theory, we can sort of tell you which is the best runway configuration to choose and what would be their environmental impacts and so on.
Yeah, thanks. And there was one question, if you could answer in 30 seconds, if you could elaborate on the potential discrepancy between emission distribution versus hotspot queuing model assumptions.
Emissions dispersion versus hotspot. I'm sorry, can you repeat that?
So the potential discrepancy between emission distribution versus hotspot queuing model assumptions. So I suppose how your assumptions in your queuing models could affect the distribution of emissions in your dispersion modeling.
Right. So in this analysis, we sort of assume queuing at certain locations. Let me pull the hotspot data quickly. So we sort of assume the queuing happens just at the 2 departure runways, right? We might have some queuing even in the ramp areas for small time intervals. We just ignore that and assume queuing primarily in the departure runways, which is true for most of the time. So, but we ignore any small waits in other locations of the airport. I think this can cause a little discrepancy between what happens really in operation and what we model using the queuing model. And this would be reflected downstream as well for estimating emissions.
Great. And if you'd like to elaborate any more, you can also respond to the Q&A just in the typing into the box, I think. But so thank you for that. Thank you, Sandeep and Emily, for a great paper.
Sure.
Okay.
Thank you.
So we'll move on to our next presenter. We have Dr. Giovanna Kuljanin. Dr. Kuljanin is an assistant professor at the Polytechnic University of Catalonia and a researcher on several Cesar and Clean Sky projects at the Icarus Research Group at UPC. Her main research interests are airline planning and operations, airline competition, and air transport demand. And she has recently broadened her horizons by initiating research on flight efficiency. So Giovanna, the floor is yours. And we do see your presentation.
It will be great if you can unmute, Giovanna.
Can you hear me now?
Yes, now we can hear you.
Okay, so sorry once again for this inconvenience. So I just said that it's my great pleasure to be together with you. And I would like at the beginning of this presentation to thank my colleagues, Jordi Pons-Prats and Xavier Prats, who are the co-authors of this paper. And the title of the paper is Fuel-Based Flight Inefficiency Through the Lens of Different Airlines and Route Characteristics. Post-operational analysis for 1 day of traffic at the ECAC level. As all of you are aware, actually, the greenhouse gas emissions from commercial aviation are rapidly increasing. For example, the aviation, according to the last report of International Council of Clean Transportation, the aviation contributes to around 2.4% in global CO2, indicating the increase of 34% over the last 5 years. However, the ATM modernization programs around the world, such as Cesar and NextGen, are trying to gradually eliminate the environmental inefficiency across different new concepts and solutions. However, the performance of these ATM solutions needs to be gradually assessed or constantly assessed in order to close the gap between the actual and the high-level targets. However, for this purpose, we have a plenty of performance-based frameworks provided by ICAO, CANSO, Single European Sky, containing a large number of performance indicators aimed for the assessments of this performance. However, this paper actually is based on the methodological framework proposed by the exploratory research project called Apache within CESAR. And the core of Apache framework resides actually in the performance analyzer, which is collecting the information from historical flown and planned trajectory, and from one side, and from the other side, from optimal traffic and airspace planner, it is receiving the information on the optimal for the trajectory reference in order to compute a family of performance-based indicators. However, you can ask the question, what kind of objective functions and what kind of optimization constraints can be included in this optimization process? In order to provide this answer, I will show you the slides, which actually shows to which extent the optimal trajectories may differ depending on the constraints imposed in the optimization problem. So as you can see, these two figures on the right-hand side depict two optimal trajectories. The red one actually optimizes the fuel consumption in the free route airspace, while the second one is optimal trajectory in ATS network route. However, both trajectories contain the information about weather, and both of them are minimizing the fuel consumption. So once we have set the constraints and obtain these optimal trajectories, we can start feeding our Apache analyzer, which can provide us with four families of performance-based indicators. Namely, they are distance-based, fuel-based, cost-based, and time-based indicators. However, for the purpose of our analysis, we will be focused only on the fuel-based indicators. So these slides provides 9 performance indicators from the family of fuel-based indicators, which will be used in this presentation. As it can be observed, different variants are proposed, aiming to decouple and to identify different sources of environmental efficiency, distinguishing those that could be attributed to the different layers of ATM, so including tactical, strategic, and all ATM layers. And as you can see, within all of these 3 sets of performance indicators, the efficiency will be further decoupled to capture the inefficiency in horizontal and in vertical domain. So let's imagine that we as an airline agree to fly the reference business trajectory. And this is actually the trajectory that NSPs and airports agree to facilitate if we are speaking in terms of CESAR terminology. But we have to bear in mind that this reference business trajectory might contain some strategic, horizontal, and vertical inefficiency stemming from the fact that it needs to follow structured ATC routes, that it needs to avoid some restricted military zones. So in other words, the flow trajectory will contain this inherited vertical and horizontal strategic inefficiency, but it will also contain some tactical vertical and horizontal inefficiency due to the ATS interventions, for example. So by comparing the different reference trajectories here, we will be able to obtain all these 9 performance indicators that we will be using in our analysis. So the first one is the tactical fuel inefficiency, which is actually calculated as a difference in fuel efficiency between the flown trajectory and the reference business trajectory. However, if we assume that we have some optimal trajectory, we will be also unable to extract the strategical inefficiency. In this case, strategical inefficiency is the difference between, as you can see here, the fuel consumption in flown trajectory and the fuel consumption of optimal trajectory. And And finally, you can also calculate the total fuel inefficiency, which is obtained as a difference between the fuel consumption and flow trajectory and the optimal one. Following the similar logic, we can also obtain the total vertical, total horizontal, and all others PIs. However, this methodology has been already presented in the previous ATM seminar, so in 2019, so I will not lose so much time on this now. However, having all these indicators explained now, we have to bear in mind that our methodological framework also enables us to generate different optimal trajectories by changing the optimization function and changing the constraints. So in this case, the optimal trajectory is actually minimization of fuel consumption, but we can adopt any others. So you can clearly see that the outcome of the PIs will be different. So the optimal trajectories are computed in the following conditions. As you can see here, structure route airspace and maximum range operation, which correspond to cost index 0, then free route airspace and the cost index 0, structure route airspace, then cost index chosen by the airspace users, and finally free route airspace and cost index again chosen by airspace users. This slide actually provides the methodology in details, but as I already told you, this is presented in the last ATM seminar, and it is also presented in several papers. So let's skip it for now to come to more interesting results. So once we reconstructed all this whole database of historical flown and planned trajectory together with the corresponding performance indicators, we decided to apply a different set of filters in order to explore the fuel-based inefficiency at different granularity of the results. So for this purpose, we analyzed the results of fuel-based inefficiency with respect to 3 different filters. The first one is airline business model. This second one is, as you can see, route length, and the final one is route frequency. So regarding the airline business models, as you already know, the most optimal trajectory from airline point of view probably depends on the underlying business models. And as you already know, the traditional classification on full service and low cost carriers might be no longer be valid in the current context of the ongoing hybridization among the airlines. And with this regard, we aim, so in the light of this ongoing hybridization process, our aim was to observe to which extent this hybridization process is entwined into fuel efficiency. In this regard, we based on the work of Magdalena and Pauzaima, who used the K-means cluster in order to provide 4 different categories of airlines. On the other hand, the route length may have a tremendous impact on total airline operating cost, and we wanted to check if there is some difference across the route with different length with respect to fuel efficiency. In this way, we divided all our routes into 5 categories, and these categories will realistically reflect the network of carriers operating at the ECAC level. So finally, the route frequency is included to see if there is a distinct behavior across the route with different frequency with respect to fuel efficiency. For example, in European Union in 2020, we had around 160 airport pairs, which had around 12 or more departures per day, and could you imagine one delay on a very high frequency route can have tremendous implication to other rotations during the day, and that's why we were inspired to check if there is a distinct behavior across fuel efficiency in terms of these different categories. And in this slide, we divided our database in 4 different categories, as you can see here in the slide. So our analysis was based on the set of 24 hours of historical flown and planned trajectory for July 28, 2016. The planned trajectories were retrieved from EUROCONTROL DDR database M1 file, while the flown trajectories were retrieved from M3 file. It's also important to emphasize that we use the EUROCONTROL BADA 4 model for aircraft performance, while the historical weather data were retrieved from Global Forecast Service. So let's start. This figure here shows the result of the fuel inefficiency in absolute and relative terms across the 4 different airlines. The optimal trajectory is constrained to full free route airspace and cost index 0. As you can see, in terms of total fuel efficiency, there is the airlines within low-cost carriers and H1 carriers have the highest total inefficiency in absolute terms, around 530 kilos, but better performance in relative terms, accounting for around 17%. On the other hand, the carriers from full service carrier group and H2, they have a lower total efficiency in absolute terms, but they have a higher inefficiency in relative terms, accounting around 20%. On the other hand, at tactical level, we can see that at tactical level, that fuel efficiency is almost 0 across all 4 airline groups, indicating that ATC is actually providing a shortcut for the most of the flights, irrespective of the airline business types. However, it's worth mentioning that the carriers from LCC and the H2 group, they have the highest negative total fuel inefficiency, accounting for minus 1%. While the carriers from FSC and H1 group, they have highest total fuel inefficiency, around 0.03%. If we want to do some interpretation of these results, we can tell that, for example, the carriers from full service groups, they operate extensive hub and spoke network, which mainly connecting secondary airports with hub airports, and which leaves less opportunity for tactical interventions. On the other hand, we repeated the similar analysis, but we constrained the optimal route to structure ATS and route network and cost index 0. Not surprisingly, the total inefficiency is generally lower in the absolute term compared to the previous case, since this case better reflects the real operational environment of the day of study. Those are the results for the fuel efficiency within different route length. Here is the distribution of the routes following their real length. So as we can see, around 37% of the routes operated within ICAG level are less than 350 nautical miles. And regarding the results, we can clearly see that there is a great difference in total flight efficiency among the routes with different stage length. Not surprisingly, the results show that longer routes exhibit higher inefficiency in absolute terms, while conversely, the fuel inefficiency in relative terms significantly drops as the length of the route increases. On the other hand, at tactical fuel efficiency, we didn't find any significant difference in relative fuel efficiency among the 4 categories, although tactical layers contributes to the horizontal efficiency gains around minus 0.1% across all categories. Finally, the slides present some results for the fuel inefficiency across different route frequency. For instance, the total inefficiency has a median around 400 kilograms for all categories, mostly due to the strategic part of the ATM. However, as you can see, the busiest the routes are, the higher inefficiency they accrue. So for the routes less than 5 departures per day, we have a relative inefficiency of around 19%, while for the routes with the daily departures between 20 and 30, the relative fuel efficiency accounts for 25%. So this was a good indication to try to deeply dig into the results for routes with very high frequency, higher than 20 departures per day, and we extracted 23 routes. However, the results show that when we consider free route airspace, the fuel inefficiency are generally higher than if we include the structural route airspace. On the other hand, if we include the structural route airspace and the cost index estimated from the executed trajectory, which we can see the drop in fuel efficiency. This is not surprising because with these constraints, we are trying to isolate as much as possible the ATM inefficiency and to remove the inefficiency induced by the airspace users or by their decision to fly the cost index, which is not zero. And finally, one nice remark here, for example, for the route between Berlin and Munich, if we take into account the structural route and cost index 0, we will have the fuel efficiency of 200 kilograms. But if we constrain our reference trajectory to structural route airspace and cost index corresponding to one chosen by the airline, we will have a lower fuel inefficiency of 140 kilograms, which corresponds to 8.2% in relative terms. Finally, as you can see, this paper aims to demonstrate the benefits of the methodology which employs the advanced parameter estimation and trajectory optimization. It is all these studies particularly relevant in the ongoing regulation toward more carbon neutral aviation, and particularly in the COVID pandemic, which severely hit the economic impact of the airline. So the conclusion can be beneficial for the airlines, which can better understand the consequences of non-flying optimal routes, but also the airlines can better assess direct operational benefits stemming from the implementation on free routes airspace, which is envisioned to be highly deployed at European and probably American level. And to better airlines to properly design their routes at flight planning stage. On the other hand, it can help policymakers to gain a valuable input for setting up the targets and ambitions for different KPIs and KPAs. And for example, in the case of high frequency flights, it can help policymakers to set some appropriate countermeasures to mitigate this environmental impact of these high frequency routes. Regarding the further research, we are currently working on a full-scale system which can digest a batch of days, which will further enable us to apply multivariate statistical analysis. We are also interested in comparison our initial results with the results obtained for US market. And finally, we will be very happy if in the forthcoming period we could do some enhancement in our methodology, especially in the estimation of the landing mass and the cost index. thank you very much, and I'm ready for the questions.
Okay, thank you very much, Giovanna. Let's see, we do have a question from the audience, and so your slides state no en route charges, and hence did you also do simulations with a certain modulated route charge? What was the structure of these? And this audience member thinks that airlines already have the incentive to fly as efficiently as possible from a cost perspective.
Sorry, just give me a second to set up my Zoom because everything disappeared for a while, and I will try to provide. Meanwhile, Xavi, wait. Sorry, once again, if I can. So could you repeat the question, please?
So the question relates to en route charges, and asks if you did simulations that incorporated a modulated en route charging. How was that structured? And
yeah, in our optimization process at the current stage, we didn't include the route charges, and we think that it is fair because sometimes the route charges may force airlines to avoid specific areas, and we aim to provide as much as possible the environmental friendly reference trajectories, and that's why we didn't include the route charges. Exactly. Your slide state no en route charges.
Right.
No, as I already answered, we at this stage we didn't consider en route charges. Thank you, Eve.
Okay. Other questions from the audience? I don't see anything coming in right now, so I'll go ahead and ask one. I guess I'm wondering from this, all of your post-operational assessment, what you sort of see as the greatest target for performance improvement, either for ANSPs or for policymakers, and what do you kind of think might be the levers for achieving those gains?
Yeah, as I told you, we were really astonished by the results obtained for routes with different frequencies. As we could see, the very busy route can have a very high impact on CO2 emissions. And in the future, together with the policymaker and as a academia, we should work on it to improve this for sure. Because could you imagine these busiest routes with 20 departures per day generate so excessive CO2 emissions? And could you imagine what can be the impact on an annual level of such operations? So for sure, if we can sit together somewhere with some NSPs and airlines on the other hand, and make some wise investigation into this route, it will be beneficial for the environment for sure.
Mm-hmm. And do you think that, I know that this framework could definitely be helpful informing performance targets. I suppose, do you think those sorts of things would be enough to influence or mitigate, or I guess manage behavior on those high frequency routes? Or are there other sort of either measures that could be introduced to try and improve the situation there?
Improve the situation on a high frequency route, or improve the situation in general?
Generally, but I guess with a focus on those hotspots, as you indicated, those being sort of driving a lot of inefficiency overall. I guess yeah, maybe this is
you know, our tool can be very useful to set the performance targets, for example,
right.
and we can estimate the theoretical benefits of it. But what is in practice at the end is another story. But at least we can try to motivate the policymakers and all stakeholders to plan in another way, which is more environmental friendly and than it is nowadays.
Okay, thank you. We have another question from the audience. So what is your view on the benefit pool, the emission savings potential in the en route phase versus the climber arrival phase of climber descent?
On the benefits?
The crew, I guess the cruise portion of flight versus climb and descent, the more terminal area type inefficiencies.
Yeah, for sure. As at the current stage, we didn't separate climb, crew, or descent. We focused on only cruise in this paper. But knowing that TMA can be a bottleneck for the majority of the cases, as a direction of further research, it will be great to explore this area and to see what is the inefficiency generated at TMA. So at the current stage, we only considered en route. And another point is that the input we used is DDR database, which is not good for TMA. I mean, the resolution of the traffic is not good, so we cannot extract this database and as a credible background or a credible database. So probably we will need to use some other databases in order to have better simulations.
Yeah, I think that's an interesting question that definitely we're thinking about in the US too, is how much, the cruise portion of flight is where you're burning the most fuel, obviously. And so improvements there may, marginal improvements there may result in greater bang for the buck, but obviously there's a lot of focus on the terminal as well and the bottlenecks that happen there. So I think that's an interesting question to think about. Another question from the audience. So you said that you calculated wind optimal routes based on GFS data. Did you account for any other weather deviations, such as around convective weather, or were your analysis stays for just all clear weather days?
Sorry, once again, I was not involved in the previous methodological development. So as far as I know, we used only one day. So the Chavi is replying. So we use the weather for that day only, if this is sufficient answer. So I have no idea on further details. Sorry.
Okay, right. I think there was a clarification in the chat as well that this was a study for one day. Though it does raise maybe a similar question I had, is if you were analyzing a day, I guess that had some sort of disruption, either convective weather or otherwise, how would that affect some of the either the methodology or the indicators that you're using? Would you be able to sort of account for that?
Yeah, okay. It highly affects. That was one of the items in my conclusion, is that currently we are working on the batch of days. So in order to include as much days as we can, to actually check these commonalities and this trend that we obtained by using only one day. So I would say that the results that we obtain are good as a first indication, But in terms of the statistical significance, of course, they are not significant because they are based only on one day. Although we have to say that this day is 28th of July, which is actually high demand scenario, but still we would need more days to fulfill the data set and to try with some regression analysis and to see if we gonna come to the same results, or at least to the similar results obtained at this stage.
Mm-hmm. And then at a sort of a more granular level, so a big discussion in terms of aviation's climate impact is contrails and aviation-induced cloudiness. So I'm wondering if you had, say in some future state, you had a capability to, I guess, avoid airspace where contrails are likely to form, and maybe that creates longer track miles or something like that. Is that sort of a, how do you think you could adapt your approach here to sort of assess that performance if you know there are maybe like I guess at a fundamental level you're just trying to avoid blocks of airspace, but that's not necessarily, that's a good result maybe, but you have to trade it with fuel and all of that.
Yeah, exactly. You have to see the results, but from the methodological point of view, for us, it is very easy to implement in our Dynamo tool, because you can specify this area as a constraint and put in a constraint and try to run the optimizer once again and see what results we can get out of it. So it's, thank you very much. We will write it down. This is a great remark for future research.
Yeah, I think it could be a good and easily adaptable application for your approach. So there's another question following up on the sustainability question. So there's a lot of talk about sustainability, excuse me, about sustainable aviation fuels and their use. Do you see, could you possibly tailor your study to stimulate policy decision makers to incentivize utilization of sustainable aviation fuels, or in light of your identified high frequency city pairs? So I guess the question is, could you kind of deploy, try to deploy SAFs at you know, to the routes that need them the most, or something like that?
I would say that we are currently engaging a very nice Horizon 2020 project called Alternate, and Alternate is actually dealing with the use of these alternative fuels. And currently we are investigating how these alternative fuels can be integrated with our Dynamo simulator in order to see the real benefits in terms of the CO2 emissions once the airline will have in place these kind of fuels, alternative and biofuels.
Mm-hmm.
So yeah, can we tailor the study? Actually, we can, and we are currently working on this in the framework of this Alternate project.
Yeah. Yes, and your co-author noted that you would love to have a thrust and fuel flow model for SAF, but that's I think that's still to come. Still have just a couple minutes. I had one last question. If I was wondering if you've shown these results to airspace users at all, or gotten any feedback, or do you plan to? Especially if you could, you know, talk to a low-cost carrier, a legacy carrier, see if this kind of jives with what they see in their operations.
Yes, I think that we will take opportunity through these expert panel meetings that we are organizing from time to time within our CESAR project and Clean Sky project. So during this period, we received very nice feedback from them in terms of operations, in terms of in terms of their policies. So for sure, one of the topic maybe the next meetings will be to discuss the results that we obtain and to ask them whether these results are useful for them, or from our side, can we do some additional work to help them in their decision, the flight planning process.
Great, thank you. And a similar one, so you talked about this this work being able to inform performance targets. Are those discussions that you've had or plan to have with in Europe about developing and using this work to inform KPAs or anything like that?
Do we use? Sorry, I didn't understand you properly. Sorry, could you repeat?
Yeah, will this kind of framework be used to inform goal setting, performance targets? Are those discussions happening that you're a part of or have heard of, or you just are have shown this methodology and it's out there as something that EUROCONTROL or whomever can pick up to help with their internal goal setting? Just wondering if you've had any sort of more dedicated discussions with EUROCONTROL or other ANSPs.
From my side,
yeah.
I didn't, but I am not aware if my colleagues and co-authors had a similar one. So unfortunately, I didn't have.
Okay, no, that's fine. Thank you.
Thank you.
Okay, well, thank you very much for the presentation, the paper, and for answering all of our questions, however silly some of them may be from me.
Thank you so much once again.
Appreciate it. Okay, so we have one more presenter and paper. We have Ramon Dalmau, who can work on bringing up his charts and his screen. I see him on screen. So Ramon is a data scientist at the EUROCONTROL Innovation Hub. His academic background is in aerospace engineering, and he holds a master in computational and applied mathematics from the Autonomous University of Barcelona. In 2019, he obtained a PhD in aerospace science and technology from the Technical University of Catalonia, and his current research interests include optimization algorithms, machine learning, and multi-agent reinforcement learning, all as applied to improving the air traffic management system. With that, Ramon, we see your presentation, and let's just confirm we can hear you, and you should be good to go.
Yeah. Thank you for the introduction, Chris. It's a pleasure for me to present the results of this cooperation with my colleagues Junzi Sun from TU Delft and Xavier Prats from the UPC. The objective of this work was to characterize the theoretical fuel inefficiency due to early descents, but also to assess the actual fuel inefficiency of these events by using real aircraft trajectories. This is the outline of the presentation. I will start by explaining what is an early descent and how it is executed by the guidance system of the aircraft, because we will need this information later on during the presentation. Then I will present the theoretical impact in fuel consumption due to early descents, which results were obtained by simulating trajectories. I will also explain how to detect early descents and how to estimate the fuel inefficiency from surveillance data. And finally, I will show some initial results from a case study using Adsb data of trajectories arriving at Amsterdam Schiphol Airport. The optimal trajectory plan for the descent phase is computed by the flight management system while the aircraft is still in the cruise phase. The trajectory plan is computed by backwards integration, starting at the destination airport and going backwards until reaching the cruise altitude. The very last two phases of this trajectory plan, if going backwards, consist of a phase at constant calibrated airspeed and at idle thrust, followed by a phase at constant Mach number, also at idle thrust, which finish at the cruise altitude. And the intersection between this trajectory plan and the cruise altitude determines the optimal top of descent, where the aircraft should set the engines at idle and start the descent in order to minimize the fuel consumption. And I said should intentionally, because there is just a plan. Then during the execution, the pilot can initiate the descent only after receiving the clearance by the air traffic controller, which actually doesn't know where this optimal top of descent is. If the ATC requests to start the descent before the optimal top of descent, then the guidance system will attempt to intercept the original trajectory plan from below. But this is not for free. Early descents are executed with a vertical speed of 1,000 feet per minute. It's important to keep in mind this number during the remainder of this presentation. And at the same time that the original speed profile is followed by using throttle control. In this way, when the trajectory plan intercepts from below, is intercepted from below, the current and the actual the current and the planned speeds are exactly the same, and the plan can be resumed at idle thrust. However, since this strategy requires additional thrust before intercepting the trajectory plan, our hypothesis is that the fuel consumption during an early descent will be higher than in an idle thrust descent. This slide compares the fuel flow between the actual early descent and the planned trajectory. Before the optimal top of descent, the actual trajectory is more fuel efficiency because the thrust is lower during the early descent phase, because we don't need additional thrust to maintain a constant altitude without decelerating. However, from the optimal top of descent down to the interception altitude, the trajectory plan is better in terms of fuel consumption because the trajectory plan was computed by assuming idle thrust. The net balance between the red and the green segments depend on the shape of these two trajectories, the actual trajectory and the trajectory plan, which are determined by the speed profile, that is the Mach-CAS pair, the mass of the aircraft, the cruise altitude, and the optimal top of descent. That is how much early the descent starts if compared to the optimal top of descent. Let's call this parameter, the difference between the optimal top of descent and the actual top of descent, the early top of descent distance. We could compute the difference in fuel consumption by comparing these two trajectories, right? In real life, however, the trajectory plan is only known by the flight management system, which data are not available. In other words, only the executed early descent or not trajectory can be observed from surveillance data, but not the trajectory plan. And of course, we cannot compare two trajectories if one of them is missing. The objective of this work was to answer the following three questions. First of all, which is the theoretical impact on fuel consumption due to early descents? The second, is it possible to identify early top of descents from surveillance data like ADSB? And finally, how to assess the actual impact on fuel consumption due to early descents by using only surveillance data when the trajectory plan is not available? This slide shows the workflow that we followed in order to answer these three questions. First, we selected a representative set of flight conditions, and for each one of them, we compared the optimal trajectory plan with an hypothetical simulated early descent. The two trajectories were computed by using the Airbus Performance Engineers Program, PEP. And as a result, we were able to characterize the fueling efficiency of early descents from a theoretical point of view and populate a multidimensional lookup table that can be queried with some observable key parameters. Given a set of key parameters that could be observed from surveillance data, that is from the executed trajectory without requiring the plan, this lookup table estimates the difference between the unknown trajectory plan and the actual observed early descent. Then we came out with a very simple yet effective method to identify early descents from surveillance data, like ADSB, and answer the second question. And finally, we assessed the actual impact on fuel consumption for a large traffic sample by simply querying the lookup table with the key parameters observed in the real ADSB trajectories. Now I am going to present these 3 steps one by one. First, each flight condition is determined by the combination of 3 input parameters: the cruise altitude, the mass of the aircraft, and the cost index. Oops. Yeah. For each possible combination of these 3 parameters, the optimal trajectory plan at idle thrust was computed with PEP, and the following attributes were extracted from the optimal trajectory: the optimal top of descent and the optimal speed profile, that is the Mach and the cars pair, and of course the optimal fuel consumption. Then, for each one of these optimal idle thrust trajectory plans, we simulated several early descents using exactly the same cruise altitude, the same aircraft mass, and using the speed profile from the optimal trajectory plan, because we know that early descents are executed by following the same speed profile that in the optimal trajectory plan. Finally, we were able to compare each one of these early descents with the corresponding idle thrust trajectory plan and compute the fuel consumption difference, and also how many feet we need to descend in order to intercept the trajectory plan, starting from the cruise altitude. Because this is the only thing that we can observe from ADSB. We cannot observe the early top of descent distance because we don't know the top of descent, but as we'll see later, we can observe the interception altitude. So we computed the difference between the optimal trajectory plan and the early descents for all possible combinations of these parameters. So we selected an Airbus A320, 4 different altitudes, flight level 300, 320, 350, and 70, 2 typical aircraft masses during the descent, 4 different cost index, and we assessed 4 different early top of descent distances. So 10, 25, 50, and 70 nautical miles. This results in 128 early descents, which were compared to 32 corresponding idle thrust trajectories. This slide shows in the vertical axis how many feet we need to descend in order to intercept the trajectory plan from below as a function of the early top of descent distance in the horizontal axis. Each row shows the results for one of these 2 masses that were considered in the study, while each column shows the results for a given cruise altitude. And then within a cell, each line corresponds to a different cost index. As expected, for a given combination of these 3 parameters, the mass, the cruise altitude, and the cost index, the earlier the descent starts from the optimal top of descent, the later the trajectory plan is intercepted from below. And interestingly, for a given mass and cruise altitude, the relationship is almost linear, and the slope is determined by the cost index. This slide shows the fuel consumption difference in kilos between the early descent trajectories and the corresponding idle thrust trajectory plan. Positive numbers indicate a higher fuel consumption during the early descent. Different from the previous figure, here each cell shows the results for a combination of mass and cost index. And within a cell, each line corresponds to a different altitude. But again, the results are shown as a function of the early top of descent distance in the horizontal axis. According to this figure, the earlier the aircraft starts the descent from the optimal top of descent, the higher the extra fuel consumption in absolute terms. We can also observe that the extra fuel consumption could be as high as 120 kilograms for a very extreme case where the descent starts 75 nautical miles before the optimal top of descent. This slide shows exactly the same results, but in relative terms. That is, the difference shown in the previous slide divided by the total fuel consumption of the trajectory plan. And the results show that the extra fuel consumption could be as high as 20% in relative terms. So far, we have analyzed the extra fuel consumption by using simulated trajectories, comparing each one of the simulated early descents with the corresponding idle thrust trajectory plan. But in real life, we don't know if an observed trajectory from surveillance data is performing an early descent, because we don't know the optimal top of descent of the trajectory plan. However, we will show that it is possible to identify early descents just by knowing that they are executed at 1,000 feet per minute, according to the flight crew operating manual, until the interception altitude, where the trajectory plan is resumed at idle thrust. This figure shows the vertical speed of an Airbus A320 with the engines at idle, assuming a typical descent mass, corresponding to the maximum landing mass. The vertical speed is presented as a function of the altitude in the vertical axis and the true airspeed in the horizontal axis. And several speed profiles are illustrated. A fast speed profile in blue is the blue line, then a typical speed profile in orange, and a very slow speed profile in gray. And according to this figure, the descent rate of an Airbus A320 with the engines at idle and with a typical descent mass is higher than 2,000 feet per minute for most operational speed profiles, which is well above 1,000 feet per minute. This indicates that an aircraft descending with a descent rate of 1,000 feet per minute, no matter its altitude or speed, is applying some thrust. In this study, we propose a very simple method to detect early descents that only requires altitude and vertical speed profile. And this data can be obtained from ADSB. You could find more details in the paper, but essentially, we process the altitude and the vertical profile using a sliding window of 10 seconds in order to identify with a linear regression whether the first segment of the descent is performed at a constant vertical speed of minus 1,000 feet per minute or not. If the answer to this question is yes, then we are observing an early descent. Otherwise, it's not an early descent. Now, let's imagine that we detected an early descent from this ADSB data using the previous method. This slide illustrates how to extract the key parameters, also from ADSB, that are required to evaluate the lookup table and compute the additional fuel consumption with respect to the unknown trajectory plan. The cruise altitude in red can be easily obtained from the altitude profile because it's the point where the descent starts. The interception altitude in orange is the point where the segment executed at 1,000 feet per minute ends. So it can be also observed very easily from the altitude or vertical speed profile. What about the speed profile? Remember that early descents are executed by following the speed profile of the trajectory plan with the throttle. This means that even if we do not have access to the trajectory plan, we know that it was computed by using the speed profile observed in the early descent trajectory. In this study, we used a two-piecewise regression model in order to detect the constant Mach and CAS segments of the trajectory observed from the ADSB data. But you could find further details in the paper. Finally, estimating the aircraft mass from surveillance data is not straightforward, especially during the descent phase when the thrust is very low. However, the theoretical results that I presented before show that the effect of the mass on the additional fuel consumption is residual if compared to that of the other key parameters like the cruise altitude, the interception altitude, or the speed profile. For this reason, in this study, we assumed a mass corresponding to the maximum landing mass. The method to detect early descents has been applied to more than 4,000 ADSB trajectories of A320 aircraft descending at Amsterdam Schiphol Airport during April 2018. For each one of the detected early descents, we extracted the key parameters following the method explained in the previous slide, and we estimated the actual impact on fuel consumption by querying the multidimensional lookup table. And now I am going to present an illustrative example and the main results of this assessment. This slide shows one of these 4,000 ADS-B trajectories in order to illustrate the procedure. The top left plot is the altitude profile as observed from ADS-B data. The top right plot is the calibrated airspeed profile in knots. Then we have the vertical speed profile in the bottom left and the Mach profile in the bottom right. The proposed method classified this trajectory as an early descent due to the initial segment at 1,000 feet per minute. And then we extracted the key parameters from the ADS-B data. This aircraft starts the descent at flight level 360 and ends the early descent segment after 10,000 feet when intercepting the trajectory plan at flight level 260. The Mach number is 0.79, according to the method that we proposed, and the CAS is 290 knots. Then, assuming a mass corresponding to the maximum landing mass, the lookup table estimates that this flight has burned 20 kilos of additional fuel, which represents a 6% increase with respect to the corresponding, yet unknown, idle thrust trajectory plan. From the around 4,000 trajectories in the traffic sample, 868 were classified as early descents, which represents that 21% of the total number of trajectories in the traffic sample. The figure in the left shows the distribution of the key parameters, so the initial altitude, the calibrated airspeed, Mach, and interception altitude of the detected early descents. And the figure in the right shows a box plot of the extra fuel consumption in absolute terms in the left and in relative terms in the right. According to this figure, the estimated mean extra fuel consumption caused by early top of descents in Airbus A320 trajectories in the terminal area of Amsterdam Schiphol Airport during April 2018 was around 10 kilos, which represents a 5% increase when compared to the fuel consumption of the idle thrust trajectory plans. The median of this distribution was around 5 kilos, which represents a 3.5% increase in relative terms. In this study, we show that early descents are common and that their impact on the fuel consumption is not negligible. These results should raise awareness and encourage air traffic controllers to respect as much as possible the optimal top of descent. And future work could also combine the surveillance data like ADS-B with ATC transmissions in order to identify the causes of early descents and maybe to identify correlations with traffic load or complexity at the airport or at the terminal area. Furthermore, future work could validate the fuel consumption impact figures that we found with FDR data and also analyze the sensitivity of the results to weather variables. For instance, by considering the longitudinal wind that was neglected in this study, or also non-standard atmospheric conditions. And finally, future work could also perform the same analysis, but for other airports and for other periods of time, in order to maybe find differences between winter and summer periods. And that's all, and thank you very much for your attention.
Okay, thank you very much, Ramon. Let's see, we have one question in the chat. I think you may have answered this. So how did you infer the aircraft mass from the ADS-B data before looking it up in your table?
In this study, we assume that a mass corresponding to the maximum landing mass for the sake of simplicity, because we know that inferring the aircraft mass from the ADS-B, especially when the aircraft has the engines at idle, is very difficult. And in addition, in the theoretical study, in which we were able to simulate the trajectories, we observed that the effect of the aircraft mass was residual if compared to that of the other factors. So this is why we assumed a constant mass, but it's true that in order to be more accurate, we should also estimate the aircraft mass from the ADS-B data.
Yes. So a follow-up question from the audience. So would pilots and air traffic control be willing to communicate over the radio about their theoretical top of descent? And I think that goes to your conclusion slide about sort of ATC, respecting the optimal top of descent point. How does that kind of communicate back and forth, I guess?
Yeah, it's true that in this paper, we assessed the effect. So we showed that is that there are some early descents and which is the effect in the fuel consumption of these early descents. But we didn't answer the question to the why. Why these early descents? And it's true that we think that ATC could try to respect as much as possible the top of descent, but of course, in order to respect the top of descent, they need to know the top of descent. So I don't think pilots should send the top of descent via communication. No, maybe Mordio could be included in the ADSB data, in the broadcasted data in a more automatic way, not through radio communications.
Yeah, good question. So another question from the audience, could this method be used to identify ATC interventions on flights before descent from recorded ADSB data? I think that's, you sort of talked about that. But.
Yeah, actually in the second point, we propose a very simple method to detect these early descents. And in fact, we believe that they are due to the ATC, because the pilot maybe would wait until the optimal top of descent, even if we don't know. As I said, we don't know the why of these early descents. But yes, this method could be used to identify ATC interventions, but only causing early descents, not other types of interventions.
Mm-hmm. Yeah, so on a similar thread, you mentioned looking at other airports, looking at seasons. I guess what would be interesting, I'm wondering if you can do it, is if you can look at a large number of airports, a large number of arrivals, and kind of, identify statistical hotspots where there are lots of early descents and they're particularly egregious, and then maybe from there get at some root causes, either airspace structure or ATC practice issues. Is this, I guess, on that scale, is this or is this kind of approach scalable to that extent, or would there be challenges or that you could foresee in doing that?
No, I don't think so. The only limitation that we have is that we can only use A320 aircraft, okay? Because the lookup table, well, not A320, Airbus aircraft in general, because the lookup table was completed by using the Airbus PEP, which only allows to make the computations for Airbus aircraft. So we could do A340, also A320, but not Boeing aircraft. But in other airports and also different time periods, it would be quite straightforward to extend this work because everything is automated. So we just process the ADSB data, we feed to the software, and it generates these figures and these statistics.
So another question about the from the audience about the sort of ATC role. So how can ATC practically respect a top of descent if it's dependent on so many factors, for example, cost index, mass, wind, etc., as you talked about, and those factors aren't just aircraft and airline and flight specific, but they can change over time depending on things like price of fuel, how that influences cost index, all of that. So I guess the question is, even if there was some means of ATC seeing what the operator says is their optimal top descent, can they really count on that being true, I guess, or how can they really act on that over the course of normal operations, I guess?
Well, actually, this is true. In fact, the top of descent could change also during the flight. Why not? So yeah, this is why it would be very important to transmit this top of descent to the ATC so that they know exactly where this optimal top of descent is. But all in all, at the end, the ATC needs to to ensure safe operations. So if they cannot respect the top of descent, they will not respect the top of descent, because yeah, in order to save 10 kilos of fuel consumption, you cannot compromise the safety.
Yeah, it makes sense. So another question from the audience, a little bit lengthy. So would your methodology capture the early descent in published procedures? So for example, in CDO procedures, early descent is often flown in a managed mode with idle thrust, and are then followed by either a level off segment or a segment of thrust descent until intercepting the optimal profile after the published constraint has been met. And this is a suggestion potentially for follow-up research if that's not something that's been taken into account yet.
Yeah, definitely. This is a very good idea, because in our work, we did not consider constraints specific to the procedure. So we assume that the procedure is ideal and that the flight management system can compute a perfect idle thrust trajectory plan. But maybe in some airports, this is not true. And we should consider this and adapt our software such that it identifies early descents by considering these constraints in the procedure. But yeah, should be possible.
Okay. Any more questions from the audience? Going once, going twice. We do still have a few minutes, but we can also just take. So we were reminded by Claudio that to rejoin the plenary, I guess, at 20 minutes after the hour to close out the day, but still an opportunity to ask a question here if anyone has one. But not seeing any, I guess I'll just thank you, Ramon, and thank you to all the presenters and authors in this track. Really good discussion and really good research presented. So thank you. Claudio, are you on the line? Yeah. Is there anything that I missed that need to close out?
Thank you very much. Thank you very much for chairing the session. Interesting topics. I hope that the answers were, well, the questions were answered.